sure it is. But it's a sampling distribution. I believe it's. No, that's old.
Sampling distribution?
Sampling distributions. Sampling. Yeah, 7. Oh, nice one. Sampling distribution. Okay. So just some jargon real quick. For starters, let's talk about parameters. Let's talk about parameters. And we've already talked about parameters. When we talk about parameters, we're talking about numbers that describe a population. Okay? Numbers that describe a population. These numbers are fixed numbers. Okay? So they don't change. If I'm talking about the population of 6th period AP Stats, and I want to know the mean height of all the AP Stats students in here, that would be one number. Okay, it's not going to change. Once I found that average is the average, always. Does that make sense?
Even if you get like more people?
Well, that would change the population, wouldn't it? But if this was the population right now, and I want to know what the average height, then that would be a fixed number. It's not going to change. Okay? Unless you wear pumps or something, I don't know. But the height will be the height. Oh, what?
Have you not seen us? We're wearing platforms that are this big.
No.
Okay, there's like
It's like 6, like 8.
It's like wearing boots or what?
they're like Converse, but they are like platforms.
Oh, wow. Now, here's the trippy thing, is that we've used it a lot. We did it in the first semester. We're going to do it a lot in the next semester. But the thing is, you never really know what this number is. Okay? I mean, if I knew the actual population parameters, then I would never need statistics. Why would I need to make assumptions about stuff that I already know? Right? Just go out and get it. So it's kind of a trippy idea, is that even though we talk about it to learn those statistics and stuff, we never really know it. We never. I mean, think about it. Like I said, if I call this the population of that I'm interested in, and I want to know your average height, there can only be one average height, isn't there?
Okay, so I think you're saying, yeah, I get you now.
So it's one number. I mean, the average height is the average height. An imaginary one. Well, technically here I could find it. But sometimes we have populations where it's impossible. If I want to know the average height of 17-year-olds,
Can't get every 17-year-old.
I can't get everybody, right? Exactly.
17-year-old in the next day.
So I really have to be careful with what I'm calling my population. Sometimes if I call my population small enough, I could probably find everything, right? Or everybody. What's up?
I don't know if it's a fixed number, so I don't know its value.
It's because, like I just said, if I'm calling this the population I'm interested in, and I want to know the average height of the students taking AP Stats 6th hour, there can only be one average, right? One average height. So it's fixed. It's not going to change. Okay? That's how we know it's fixed.
So we have to find its value.
Huh?
So then we'd have to find its value that way.
We kind of would, but we're not really. It is possible to do parameters if our sample size is small enough and it's reachable. Okay, you know, if I said I wanted to know the average height of 17-year-olds, could I really find that?
No.
No. No matter how hard I try, it would always just be a statistic. Okay, so and that comes up a lot. So here, let's talk about what that is. Statistics. When we're talking about a statistic, then that's a number that describes a sample. Okay. That number can change. And that changes from sample to sample. So let's say, hey, you know what? I want to know what the average height of this class is, but I don't want to measure everybody. So I'm going to sample 10 of you guys, and that's going to be the average. Does that make sense? So if I grab 10 of you guys, huh? Yeah, it's a little piece of it. It's a chunk. It's a sample.
That's what makes
Okay?
it a statistic.
That's what makes it a statistic. So I would take 10 of you guys, and I'd find your average height. And let's say, you know what? I took 10 people, and it turns out that the average height was 5.7, okay, feet. Okay, so let's say it was 5.7 feet. Now, I threw you guys back in. If I drew another set of 10, would I get the same average again? No. Maybe, but probably not, right? So that's what that means. That number can change from sample to sample. Maybe the next time, maybe it wasn't 5.7, maybe it was 5.73 feet, okay, or 5.5, or maybe 5.0, okay. It just really depends on that specific sample. So that's why this number is not a fixed number. It can change from sample to sample. And the truth is, a lot of times when we're working with data, that's what we're actually working with. We're working with samples of data, and we're making our decisions based off of that so that we can make an estimate of the unknown parameter. Questions? Don't wear yourself out. We'll get to do that later on.
Really?
Yeah. Okay, not today, though. Trying to do all that today. All right, are we good here?
Wait.
Okay. I can wait. I got one. I got one.
My grades for, I just want to say that I never saw it.
It's your grade.
I know, but you said don't touch my phone.
No exceptions.
Well, why don't you touch your phone first and then ask for permission?
MEG.
Oh, mine is figured you say yeah.
No.
What? Are you seriously catching?
I'm going on to the next slide. Okay, so let's compare the two, okay, so you guys know. Parameters are talking about population, and that's kind of nice to kind of know because P, population, parameter, population, statistic, starts with an S, sample starts with an S, parameter, population, statistic, sample. Now here's some things that you need to know though. When we're talking about the mean of a parameter, we use this symbol called mu, Greek letter mu. If we're talking about a standard deviation of as a parameter, then we use this symbol called sigma. And if it's a proportion, then we're going to use p. Understand? Now sometimes they might not use that. They'll probably use words and say, hey, the true mean is this, or the true proportion is this. Whenever they use the word true, then that's a parameter. The true mean would be a parameter. The true proportion, the true standard deviation, those are parameters. On the other hand, statistics. Now, of course, X bar, I couldn't put the symbol in there. That's X bar right there. You see that symbol? That's talking about a statistic. That is the mean of a sample. The standard deviation is S, but if we're talking about a proportion, then we're going to use this symbol, which is a P with a little hat on top of that. That's called a P hat. Math don't like hard. Or you can call that fat. Pretty hot and tempting. Questions on those? One Mississippi. Huh? I will. That's actually going to do next. Thank you. Can I talk while you're writing?
Yeah.
You be good? Okay. So, the question was explain proportion. How many types of data do we have?
Two.
There's two types of data. What are they?
Categorical and
Quantitative and qualitative.
Qualitative and quantitative. Categorical is qualitative. That's fine. Okay. What type of data can I use this with? Quantitative. Quantitative. Quantitative.
So can we just say that?
What about standard deviation? Well, same thing, right? Because it goes with that one. Well, if we don't have, then we have this bad boy. Okay? Then we have proportion. Well, I can't do math. All I can tell you is that this one would be used for qualitative data. Because I can tell you, hey, you know what? 3/5 of the people like ice cream or lactose intolerant. Okay? That's a proportion. Okay? So when we're talking about proportions, then you should understand automatically that the type of data that you're working with is qualitative or categorical in nature. Okay? And again, if we say, you know what, the sample mean was 5, the sample mean is 5, then you would understand that that is a statistic. Okay? Questions on this slide?
What about, so, statistic would just be the opposite when mean standard deviation, it would be qualitative?
No. No. Same idea. These two are still, oh, sorry, I should use the red. These two are still quantitative in nature, except these two talk about statistics, while these two are talking about parameters. Okay? Now, here's proportion, which is P, but if I'm working with a statistic, then it's a P hat.
Hey, can you give another example of it?
It's just a proportion, really is. Let's see here. Actually, we'll be doing some in here. We'll do some on the presentation so you can see it, okay?
Okay.
Because whenever I want to think of them off the top of my head, you always shoot them down. So let's move on here. Let's talk about sampling variability. If you're given a sample from a population, your sample might not match somebody else's, so you need to understand that those statistics can change, right? Because if the mean can be different, then you can have a different standard deviation as well and all that good stuff, because it just really depends on this luck of the draw. Does that make sense?
Yeah.
Okay, so it really is just like the luck of the draw. So whenever they say, hey, can a mean change? You say, yeah, the mean isn't true because of sampling variability. This mean can be very different from this sample, or from that sample, or from this sample. Okay? No, of course not. So we shouldn't expect statistics to be the same from sample to sample.
No.
But they will behave the same way. Okay? Now, because it could turn out that two means are the same, but their variability is different. Maybe some of them are really close together. Let's see here. Let me see if I can show you that. So we could have a sampling that looks like this, okay? Where the mean is here. But I could also have a sampling that looks kind of like this, and the mean is still the same. Okay, so you might get two means that are the same, but because of the nature of the numbers of one distribution, there's much more variability. Okay, so it really just, that stayed up there, it's sampling variability. From one sample to the other, the numbers might be closer together or much more separated, giving you more variability. Make sense though?
Yes.
Alright, can I move on? No?
I'm not ready, but.
What's
Oh,
that?
yeah, I gave that to you.
Oh, thanks. So it's, I feel like you leftovers, bro.
Pretty much. Could have given it to someone else.
I was the teacher for 5 seconds, I should have reminded.
Call me on my cricket. Oh, man, so that was so dead.
You saw it? No, because he hit you with volleyball.
Moving on. Sampling distributions. The sampling distribution of a statistic is a distribution of values taken by the statistic in all possible samples of the same size. So let me say that again. A sampling distribution is simply takes on all of the values that are possible by the same size sample. I know it sounds weird. Let me see if I can explain it to you. Here is my raw data, right? Raw data is composed of my values. Everyone understand that? Bap, 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 bap. So there's my raw data. That's the actual distribution. The very first distribution. Stop. Pay attention. You need to listen. Janessa. Distribution. Okay? Now, what a sampling distribution does, let's take sample size 5. Is that cool to everybody? Sample size is 5. So I'm going to say, okay, 1, 2, 3, 4, 5. Just so you know, those were chosen randomly, okay? So from those 5, I add them up, divide by 5. It's going to spit out an X bar, correct? That makes sense? And guess what I do? I throw them back in, and I pick another 5. 1, 2, 3, 4, 5. Boop, spits out another X bar.
Oh, damn.
Right?
Wait, do you eliminate the numbers you already picked?
No, they go back in. They get thrown back in. So I throw all 5 back in. I've got my full distribution again. 1, 2, 3, 4, 5. I pick another one. There's another X bar.
So it's basically the mean of a sample from a sample.
The mean of a sample
From a population.
from the population. Right? And then I do it again. 1, 2, 3, 4, 5. Boom. That's another 5. Oh, it lands here. 5 more. Boom. It lands there. And I get all these X bars.
So it's basically just saying like the different combinations of mean.
Every single possible one. Yes. That's what a sampling distribution is. Okay? It takes on all, every possible. It takes on all possible samples from the population. Okay? And you're going to get another distribution. Okay? But this is called the sampling distribution. Well, that is
Population.
that's just the population distribution. Okay? Questions there? He's not recording. What's going on?
Go back.
Oh, oh well. Hopefully you paid attention. Sorry. So let's take a look at this distribution. Now this is a simple uniform distribution, right? Has the digits from 0 all the way up to 9. But what if I were to draw 2 of them? Okay? So I could turn out to get 0 and 2. I would find the average of that, which would be 1. Does that make sense? So this kind of is going to give you an idea. So I'm going to pick 2 of these numbers, and I'm going to get a chart that looks like this. This is every single possible combination. You agree?
Yeah.
Okay. So if I take a look at every possible combination, that is what makes up my graph, or my sampling. Now if I were to graph these, boom, it would look like this. Go ahead. Yeah, 2 of the numbers at a time. So if I picked 0 and 0, the average is 0. If I picked 0 and 1, the average is 0.5. That makes sense?
But if you
Uh,
got 1, 0, it's a different.
If I picked 1, 0, it's still 0.5, see?
Well, I mean, like, would you use it?
Yeah, you would still use it because it's different, right? It's a different set. So if I take a look at the distribution or the sampling, it looks like this. And if I look at the, what?
Every time?
Well, for this distribution, it's going to look like that. Okay? But what shape does this take on? It looks approximately what? Approximately normal. And if things are approximately normal, then I have tools that I spent a full semester at the beginning of the school year looking at on how to use my z-table and all that good stuff to make predictions. So that's why we wanted to have that. Okay, questions on that? So sampling, distribution.
I don't have like a question, it's all just doesn't make sense yet. But I'll get it.
Okay, cool. If it doesn't make sense, let me know at the end, okay? Let's take a look at this, because I want to talk about something else. Are you really just making tortillas right now? That was, okay, because you're kind of distracting me. So let's talk about sampling variability and standard deviation, cool? So here's an example. Television executives and companies who advertise on TV, they're interested in how many viewers watch a particular television show. According to 2001 Nielsen ratings, Survivor 2 was one of the most watched television shows in the U.S. during every week that it was aired. Okay? So right now what I want you to kind of think about is variability. Now, let's take a look at this. Let's suppose that the true proportion of adults who watch Survivor 2 is 0.37. For starters, what does that mean?
I don't know.
37.
37% of adults.
37%
Of U.S. adults watch
Survivor.
Survivor 2. Okay? That is the parameter. That's saying everybody that's a U.S. adult, 37% of you watch Survivor 2. Cool? Now, let's say I want to do a survey, and I wanted to survey 100 people. You understand that? So I surveyed, my sample size is 100. So I want to survey 100 people. But I want to do that not just once, I want to do it 1,000 times.
Oh, damn.
Why didn't you just do what?
Well, because what's going to happen with these 100? What am I going to do with these 100?
Make a sampling distribution. You gotta put it back in.
Yeah, these 100 are going to give me one statistic, aren't they?
Oh, okay.
So do I really just want one
So you're
statistic?
doing a different 100 every time.
Exactly. So how many surveys am I technically doing here?
That's a lot of zeros.
Yeah, 10,000, right?
Yeah, 2000.
Oh
I technically have 10,000 surveys done. But how many points do I have on my sample?
That's 100,000.
Well, here's the thing though. Because I'm using the same population, can I have grabbed some of those people more than once?
Yeah.
Yes. Okay, and that's okay.
So they're different groups of people.
It's just, yeah, it's 1,000 different groups. Doesn't mean that some of them are not re-included. So, here's what the distribution looks like. What did we say the true mean was? 0.37, right? Did we capture the true mean?
Yeah.
Yep, sure did. It's right in the middle. So, yay us. Now, yay us. Let's take a look at another problem. Television executives and companies who advertise on TV are interested in how many viewers watch a particular television show.
Wait,
According to 2001 Nielsen ratings. What?
what's the true mean? The P equals 0.37.
Yes. So what is that telling us?
What does P mean?
Proportion. So out of all U.S. adults, 37% of them watch Survivor 2.
So 37 was the mean of our sample?
It's not the mean. It's the proportion of that.
Wait,
Yeah.
so what are they wants to do? Find a proportion of it?
Right, what are we talking about right now? What did I say? Let's talk about variability. Okay? So I want you to focus on variability. You see what our variability was here? Everyone see that?
So you can talk during class.
It should be.
But then the proportion is bigger.
But also understand this. Do we really know the true P? No, we don't. Okay? This is why it says, what's it say here? Suppose. Okay? Can we ever say it is? No. Okay? So anyways, moving on. And what are we focusing on? Variability. So, let's take a look at this problem now. Yes, it's the same problem as before. Except, suppose that this time, instead of asking 100 people, I asked 1,000 people, but I still do it only 1,000 times.
A million now.
I would have more surveys, technically, yes. Okay? But what changed from this scenario to from the last scenario?
Your parameter.
My sample size. My sample size went from 100 to 1,000. How do I expect that to affect variability? It will be more accurate, okay? The larger the sample size, the less of something. And what is that something? Variability. Watch this. There's my second one.
Didn't you tell us that?
Okay.
Remember?
Here's the first distribution where I had sample size was 100. My variability went from 0.37 all the way down to
Different variation.
0.22. The higher my sample size, the less my variability.
That's chapter 1.
Okay? It is chapter 1 stuff, but I'm just repeating it, okay? And it's true stuff. The higher my sample size, the less my variability. So do we always want to have larger sample size? It would be not. Why not?
I mean, yeah, but we can't always have it.
Why not? If you tell me you can't have it, you must
Okay,
have
fine,
it.
never mind. You could always have it.
No, but you can't always have it.
That's what I just said.
Okay? Because think about this. Okay? The first time, how many people did I sample? 100. If I went from 100 to 1,000, what needs to happen? Now use common sense here. I surveyed 100, now I want to survey 1,000.
You gotta find 900.
I need more people. And more people, what does that mean?
More accurate, like
More people that I'm getting to do this for me.
More
More people that I have to
Higher.
pay,
You go survey.
right? And if I want to take a survey, I might even have to give them a little something. But if I want larger sample sizes, that means more money as well, doesn't it?
Yeah.
Okay? So you want to be careful there. If you want more accuracy, you're going to have to sacrifice a couple things. More money. And if you want to waste less money, then you're going to have less accuracy. Make sense?
But then you can just lie and say
There was one that used to get in the mail, be like, hey, take a survey and accept this dollar as a gratitude, and it's by a seller or something. I want one of those.
Weren't you telling us like last semester?
I got $1 for the Coke machine. Thanks.
Mr. Munoz. Remember like last semester when you were telling us about like when we were talking about gambling and then like how like if you say you're to flip a coin and like at first you would get like a fail, then you would fail, but as you kept going, it kept getting like smaller until it.
The expected value.
Is that the same thing?
No, it's a little different, okay? Thank you. Thank you, Sriracha. So, tumbling toast. So we could take a look at this, but this was kind of your question here. So, a piece of toast falls off your breakfast plate. Is it more likely to fall butter side down? Now, Murphy's Law says that yes, it does. However, science correspondent Robert Matthews says that the height must be typical. It must be of a typical height so that the toast has time to rotate. That makes sense, doesn't it? Okay. So Mr. Matthews tests this claim by arranging 150,000 students in Great Britain to carry out the experiment of tumbling toast. Assuming scientists are correct, the proportion of toast that will land butter side down is half. And what is that saying? That the true mean of toast that will land butter side down is how much? 50%. Now, here was the discussion we had last period. Is that really a true proportion? Why not?
Because it's not everyone in the whole world. Every piece of
Not everyone, not every
toast.
toast. It's not every piece of toast. How much toast did we use? We only used 150,000 slices of toast. Okay? It could be. But as long as they're butter. So, go ahead. Oh, there's a difference because of the grains, right? Yeah. Okay. So that was a discussion. It was just,
We took 150,000, put butter on one side and see if it would land butter side down. But it says according to Murphy's Law, it says yes, it would land butter side down. But this says it's 50%. The probability is 50%, which wouldn't that violate?
is it the probability?
Yep.
The proportion. Okay. It doesn't violate Murphy's Law because Murphy's Law says that if you do that tumbling toast, then it's going to land face down. However, according to Robert Matthews, what must happen? Okay, if this is the floor and I kind of tip it over, is it going to have enough time to rotate, to flip? So, yes, Murphy's Law is true as long as the toast is at a typical height. Okay, and typical, it's up to you. What do you want to find that out?
I know you probably went over this, I just kind of think what it,
Is that true?
definition, but like, what is Murphy's Law?
Salty Cheeto. Is there a question you can have, Saltito? Because you can ask me. I'm okay with it.
No, sorry.
Wait, I have a question.
Hold on, Ben had a question first. Go ahead, Mike. Ben.
Whatever, at some point, I just can't think of what it is.
Well, let's let Ben ask his question and then you guys can answer your question. Mike, Ben? All right. Go ahead, Magic Mike.
I know you guys probably went over it at some point, I just can't think of what it is. What is Murphy's Law again?
I don't even know what Murphy's Law is.
Isn't it whatever can go on wrong will go wrong?
Oh, yeah, that is. Why does that have to do with butter?
That's what we were talking about.
I think,
Okay,
I
well,
think they meant like.
anyways.
Gotta look at
Okay. Let's talk about the variability of a statistic. Now, variability of a statistic is described by the spread of its sampling distribution. This spread is determined by sampling design and size of the sample. Larger samples give smaller spread, less variability. Now, here's a rule for you guys. As long as the population is much larger than the sample, at least 10 times as large, the spread of a sampling distribution is approximately the same for any population. As long as the population is much larger than at least 10 times as large, then the spread of a sampling distribution is approximately the same for a normal distribution.
So,
That's what that's saying. So, if you're looking at sampling distribution and your sample size is, 10 times your sample size is larger than your population, then you would say, here, let me mathematically put it up here for you. your population needs to be greater than 10 times the sample size in order for a sampling standard deviation to be the same as a standard deviation for another population. Yeah?
So if the population is 110,
So here's what I'm saying. Let's say we're talking about, let's talk about toast. We just did toast, right? Population needs to be greater than 10 times 1,500. 1,500, 1, 2, 3, 1. Oh, did I do that right? Oh, too many zeros. So 1, 2, 3, 1, 2, 3. So do you think that there is more than 1,500,000 pieces of toast out there?
Yes.
possibly.
More, surely, right? Surely there is. So if there is, then you can say that the standard deviation of your sampling is going to be pretty much normal. Does that make sense?
We don't move on.
That's the rule. That's the one you really want to know. Here it is right here mathematically in short terms. Population needs to be greater than 10 times sample size.
So basically you're saying if the population is larger than the sample than the variation called the t.
Then you can use the formulas for normal distributions for exactly distribution. Yes.
If population is 10 times less than
Right. You can use here. You guys find your formula sheet? And then under section 3 it says differential stats. Oh, we'll talk about it later. It's okay. Here, we'll just get through this. Well, don't worry about it. Here, let's do this. Can I move on? Okay, so let's talk about this slide. What the heck? Oh, it stayed with the writing. And I think we also talked about this as well. Do you guys remember talking about what bias was? Okay. If we have a distribution and we want to consider it unbiased, that means that if we have a normal distribution, our sample should also have the same mean. Okay, that is unbiased statistic right there. If it's off a little bit, then you say there's a little bit bias. If it's a lot off, then it has a lot of bias. Okay? I'll show you some images right now. This is something, do I need to wait a little bit? More. Okay, so take a look at this image. The guy shooting here, was he accurate?
Yeah. Yes, he was.
Yeah.
Was he accurate?
That's a great move.
He was precise, but was he accurate? No. So if you have, this has high precision, but low accuracy, correct? We actually call this high bias. Why? Is the center of this where it's supposed to be? No, so that's bias. But there's low variability. See how this, we're nice and tight, close together? Okay? In a cluster, good. How about this bad boy?
This dude's all over the place.
Low This has low precision, high accuracy. Okay, because where is the center of all those points? Boom, right on the bullseye. This would be called low bias, high variability.
Wait, low bias, why?
Well, remember, we want the center of this to be at the center of this, don't we?
Yes,
So if I found the center of all those points, wouldn't that be on target?
I do, I believe.
Yeah. Well, take a look at this picture. What do you call this?
That's inaccurate.
That's just wrong.
A bad shot.
That's just wrong.
He's blind.
High variability, high bias. And here's the one we want. Right there. Low bias, low variability. So how does this translate to distributions? Here's the 4 images. Can you identify each? Let's take a look at A. What do you call A?
That's high bias,
Low variability. Wait, no.
High
yep,
variability.
high bias, low variability.
High bias,
Low variability.
high variability.
So,
See how they're all spread out? It's
Wait, which one are you pointing at?
A. There's blocks here, there's blocks over there.
Aw, dude, you showed us 4 and there's 4 pictures up there.
Yeah, so this is high bias.
That's
High
high
variability.
bias, high variability, right there.
No, where's the middle of those bars?
D.
So low bias.
There's the bar, right? So there's a mean, so that means that my bias is low, but because they're so spread, got high variability. Here, my center is like right about here somewhere, right? That's bias, and they're all over the place. Look at this one.
That's high bias, low variability.
And this one?
That's low variability, low variability.
That's the money shot right there. That's the one we're looking for, right?
Low.
Low, low. Low, low. Low, low. Chicken and waffles.
Ooh, that plays
Oh, that makes us done. Yay. And this, I don't even know what it's reading.